Well, in order to function, if you will, with the kind of mathematics we're learning at this time, you have to have a certain number of facts that are in a bag that's in your mind somewhere. A certain number of functions in particular that you know extremely well. In fact, you have memorized all the basic facts about them. So, what I'm going to do now is tell you about some functions that you need to commit to memory and practice enough with so you can immediately draw their graphs, know the domain and the range of these functions, all the basic properties. So, a library of important functions. Now don't worry, there aren't very many of them at this stage, but these are ones that you, if you become familiar with them, will make the work much, much easier for the rest of the course. So, after I'm finished with this, you'll have quite a bit of time, I hope, to actually practice with these and quiz yourself on them. So let's start looking at this. A library of important functions. All right. What will we see as I go through and I expose you to the entries in this library? Well, the first thing you will see is f, the function. Okay, I will give you the name of the function and its actual form. These will all be nice algebraic forms. The second thing we will look at, because it's very important to visualize the function, we will look at the graph and what a typical point looks like. Now, of course, all the typical points will be of the form x f of x. I'm going to write that down so you can start thinking about it that way. The third thing we'll see is the domain of f. The fourth thing is the range of f. These are particularly easy functions to find the range on, so we'll do that. And we might as well, while we're there, check and see if they're odd or even. Okay? So this is what we're going to do as we explore this library of functions. Now, what functions are in this library? Well, here's the library. Let's just look at it. There's the library of functions. Not a whole lot of books here. The functions at the left, you notice in the big thick book, are the line family. We'll talk about various kinds of lines. Then we have x squared, that family, which is just one function. Then the x cubed function alone, the square root of x function, the 1 over x reciprocal, or if you like, the flip over function. And then over here on its side, because it's a bit of an oddball, the absolute value function. Okay? So these are the functions that we're going to be looking at right now. Also, I'd like you to recall what the notions of domain and range actually mean. So I have a couple of pictures here. This is another way to think of domain that wasn't mentioned before. The domain of a function can be thought of as its shadow on the x-axis. So imagine, if you will, that light is coming parallel to the y-axis, both from above and below, and creating a shadow of the curve. That's what these little arrows indicate here, a shadow of the curve on the x-axis. That shadow is the domain of the function. It is the shadow on the x-axis. So there's a nice way to see the domain of a function. You just sort of kind of squash the function down onto the x-axis. Likewise, you can go ahead and call the range of a function what happens when you take shadows that are horizontal. Imagine that the function is sort of squashed down onto the y-axis. Now along the y-axis, you get this region, which is the range of the function. The shadow on the y-axis from these horizontal rays of light. So I think those are nice ways to visualize the range and the domain of functions. And I'll bring these back if we need to as we go on. All right, now we want to go into this library of functions. The first book we want to open is the line family book. And we're going to look at several entries in that book. First, we're going to go ahead and look at general linear functions. Of course, linear means line. And the general form of that function, of all those functions, will be f of x equals mx plus b, where m is the slope, of course, and b is the y-intercept. The domain of lines, the domain of a function like this, for any m and b, is simply all the real numbers, because you can put any number in here for x and get a number mx plus b. The range of the function is also all of the real numbers. There are no limitations. So these things hold for all lines. Now I say that because we're going to look at some special cases of this family separately on separate pages. So let's see if we can go ahead and draw a few of these. We've done this before, but let's go ahead and toss in a couple here just for fun. We might have one here with a slope that is greater than 0, so it's an increasing function. Okay, this repeats, as I said, a picture I did once before. Now in this context, m2 less than 0 would be a decreasing function, decreasing line. And then, of course, there are those lines that are constant, passing through some point up here, say B. This is where m3, say, is 0. Okay? And that is a constant function. Now there's some of the different kinds of lines that are members of this family. What do points look like that sit on a line? Well, all the points on lines look like this. They're x, mx plus b. The y-coordinate always looks like what f of x is, of course. So keep that in mind, x, mx plus b. Now, as I said, there are some members of this family that are particularly important, so I'm going to single them out. The first one. So this is the line family again, and one particular member of this is what we will call the identity function. Now, what does that mean? Well, you can think of it as the function that doesn't do anything to a domain element. F of x equals x. The x goes in, the x comes out. There is no change. And of course, this is a line. This is a line, just for the record, where m is equal to 1, the slope is 1, and b, the y-intercept, is 0. So this is a member of the line family. The domain and range are going to be the same. They are real numbers, all real numbers in both cases. You'll also notice that this is an odd function because it is a classic case. It's an odd power, x to the 1. What does the picture of this look like? This is one of those you need to memorize. This is f of x equals x, so all points on this line will look like x, x. Well, that is exactly what is sometimes called the 45-degree line. That's 45 degrees, so this is the 45-degree line. Okay? So f of x equals x is this line. And that's one of the most familiar lines we'll be looking at. It's the identity function. All points on it have the form xx. Okay, there's one more, and this is actually its own small family of lines that is underneath this larger line family. And those we saw pictures of before. These are the constant functions. These figure quite often into what we're doing, so let's go ahead and just mention those for the record. What do they look like? F of x equals b, some constant. Now, of course, what that means is, well, let's see, put this in the form that the line takes on, mx plus b. In this case, the m, the slope is 0. And of course, the b is itself. Now, what does this mean? This means that the height of the function, the y value for every point on this function, is b. It's always the same. So it's always going to be the graph of a horizontal line. All points will have the form xb. Notice that this will not change as x changes. So if we look at pictures, there's my x and my y. If b happens to live above there, then here's the graph of the function. If b happens to live below, b is a negative number, then here's the graph of the function. Okay? Horizontal lines. Constant functions have graphs that are horizontal lines. Okay, let's move out of the first book, which is the line family, into the second book, which is the square function. That's the name we'll give to this. The square function. That is the function f of x equals x squared. Another function we've already seen. What is the domain of this function? Well, you ask yourself, what would have to be eliminated? What number can you not square? Well, there isn't any. You can always square a number. So that means the domain of this function is all real numbers. What would the range of the function be? Well, you have to ask yourself, what numbers are squares? Well, if they're squares, that means they can't be negative. They can, however, be 0. If x is 0, x squared is 0. And they could be positive. So it turns out that the range is all the numbers from 0 to infinity, including 0. And in the picture, it will look like the part of the y-axis that starts at 0 and goes up forever. Also, since this is an even power, this is a classic example of an even function. What does it look like? Here is its graph. We've already seen it once before. It looks like that. It's what's called a parabola, which we'll study later in the course, but there's its graph. There's the y and the x-axis. It is symmetric from side to side because even functions are symmetric with respect to the y-axis. So there's a nice parabolic shape. Now we're going to do a lot with this later, so this is something you want to commit to memory. And as I say this, and later on I will show you more, the kind of pictures you want to draw now are these freehand pictures, the same kind of pictures that I'm drawing. You want them to be qualitatively correct. You want them to have the correct shape, and we will talk about that later. Here is the next book in the library that we're currently looking at. This will be called the cube function. Well, you know what this probably looks like. F of x equals x cubed. Again, this is something we've seen. The domain of this function is all real numbers, because all real numbers, of course, can be cubed. And the range of the function, well, cubes preserve negatives, so you can get negatives here. It turns out that the range is also all real numbers. And since that's an odd power, this is a classic example of an odd function. What does the graph of this look like? The graph of this looks something like that. As I've said before, there's y and there's x. A typical point on this curve will be of the form x cubed. And just for the record, let me go back to the previous one. The square function, very different picture. And I forgot to put here that all the points on here are of the form x squared. So points on the cubic have forms x cubed. And this really flattens out here in the middle. It doesn't look like that here, but it does kind of flatten out just for the moment it touches 0. All right. Well, let's move on to the very next entry in the library. This is the square root function. This one turns up a lot also. It has peculiarities of its own. The square root of x, f of x equal to square root of x. And remember that I'm always putting tails on my square roots so that I don't lose what's underneath the square root sign. The domain of this function are all the numbers that are allowable in square roots. Well, this is an even root, so I am allowed to put 0 in there, or positive numbers, but not negative numbers. So my domain is 0 included all the way out to infinity in the positive direction. So if you look on the x-axis, kind of little picture like this, starts in 0 and goes to the right forever. What will the range of this look like? Well, the square root of x is by definition the positive square root. And the only time that would be 0 is when x is 0. It will never be negative. So the range turns out to be the same thing as the domain, from 0 to infinity, including 0. And the picture you might draw for that is all the range elements starting at 0, y values, and going upward. This function is not even, and it is not odd. And I will leave you to check that. Very easy to check, mostly because you can't even do the test. The test requires that you look at f of minus x and f of x. Well, one of those two numbers, x or minus x, will be negative, and the square root is not defined for a negative number. So that means that you can't even apply the test. The actual sketch of this looks like the following. It starts at 0, there's a point there, and it simply goes up in a curve that looks like that. This is actually part of a sideways parabola, and it will go off to infinity in that direction. What do points on this graph look like? Of course, they look like x square root of x. Now, let me just put down for the record that you could write that x to the 1/2 power if you liked exponents. And the square root function could have been written as x to the 1/2 power also. That's just a matter of taste and convenience in given circumstance. Okay, we have more in the library before we rest and practice with these. The next function in the library we might call the reciprocal function, if you want a fancy name, or you might call it the flip-over function, because that's what it does. It flips numbers over. F of x equals 1 over x. Now this one we know that the domain is restricted, something we've looked at already. The only thing that is restricted is that the x cannot be 0 because we can't divide by 0. That's undefined. So this would be the set, using that set builder notation, we get to practice that again. Set of all the x's in the real numbers such that x is not equal to 0. Likewise, the range will consist of the same numbers, because 1 over x can never be 0 either. This is an odd function because it's involved with an odd power. And again, I'll let you check that yourself. It's very easy to check and good practice. What does the graph of this look like? Here's x and here's y. Well, it is asymptotic. That means that it approaches the y-axis and the x-axis forever, but never touches them, in both directions, just like that. You can see that it is odd because it is symmetric across the y-axis, across the origin there. Any point here has a corresponding point on the other side. There is another way to describe this function as a hyperbola. I won't bother with that at the moment, but if you've heard that name, that is indeed correct here. It's simply not going to be a word that we use. What do points on this curve look like? X over 1 over x, of course, but if you like negative powers, which I don't, but you can, if you like, write it as x to the minus 1. It is better generally to write 1 over x. There are occasional cases where x to the minus 1 would be nicer. In either case, this is the reciprocal or flip-over function. Now, this has lots of nice features that we'll be talking about at length. All right. Well, there's one more member of the library in the book that was slanted to one side. That's what I'm calling here the absolute value function. The absolute value function. And let me point out that when you type this into a calculator or a computer, very often you won't use the symbolism I'm going to write down here. You'll have to write something like ABS of x. Now that stands for absolute, of course. So I might just point that out, put it here in parentheses, so you can keep that in mind. Generally, however, when we're writing things by hand, we write the absolute value function just like that. And absolute value is, as we defined it a very long time ago. The domain of this function f are all the x's that you can take the absolute value of. Or remember, our first definition of absolute value was that this was the distance of x from the origin. Well, every number has a distance, so the domain of f ought to be all the numbers, the real numbers, and indeed it is. What about the range of f? Well, the absolute value is a distance. A distance can be 0 or positive, but never negative. So that dictates that the range is from 0 to infinity, including 0. And of course, on the y-axis, that would be my little schematic diagram here, starting at 0 and going up forever. This is an even function. Okay, you could actually try that and see that this is even. It's easy to see that that's true because x or minus x will give you the same value in the function. What does the function's graph look like? Well, it looks like this. A 45-degree line coming in from the left and going out to the right. In other words, it's a V shape. And this angle in the middle is indeed a right angle. This piece on the right is really a piece of the y equals x curve. Just the part starting at 0 and going off to infinity. The other side is a piece of the y equals minus x curve, coming down and stopping at 0. The two together, the v, is the absolute value function from x-axis and y-axis. And points on it, of course, look like x, absolute value of x. Now we're going to explore this function again in a little bit. We'll reinterpret it. Right now this is sufficient, and you should have a good sense that the absolute value is this v-shaped function. Okay, well that's the last of the library of functions. Let me go ahead and give you a piece of advice, or a couple of pieces of advice now. First one is the one I've been saying all along. Memorize these functions and their graphs. If you know these functions and their graphs, you can function much more quickly in the kind of college algebra we'll be doing later. What are we going to do later with these? Well, one of the things we're going to do right away is move them around. Later, we'll alter them. And not only move them, we'll do other things to them. Let me give you an idea. We're going to do something that we'll call later shifting, which means we're going to move them either to the right or to the left without changing their shape, or we'll move them up or down. That'll be called shifting. We will do something that we'll call stretching. And you might imagine that we take the function and we pull it outward. We'll be doing something that we call compressing. which is the opposite of stretching. Imagine that you take the function and you squeeze it inward. And then we'll do something that we're going to call reflecting. That's when we take the function and we flip it across the x-axis, or we look at the y-axis and flip it across the y-axis. Now these are all operations we will perform on these basic functions. The basic functions will be the place we start, and you will need to know what they look like so that you'll know what happens to them after we alter them. Okay, now you've seen the entire library. It's time for you to look at these functions, graph them on your calculator, draw them by hand. Be sure you confirm that the domain and the range are what I said they were, and that the functions are odd or even as I indicated. And make sure that you get a good sense of what they look like before we go on to anything else. Now, beyond the library of important functions, which we've just looked at, there is another class of functions. These functions are functions that are made up of pieces of these important functions and other functions. And they are naturally called piecewise defined functions. So let me talk about how one would do that and how you write it and then graph the pictures of such functions. So let's look at piecewise defined functions. Here is what I want you to do. I want you to imagine that the plane, okay, this plane of this paper is being sliced up, okay. Imagine the plane is sliced up, or cut up if you like, into vertical strips. So we're taking vertical strips and we're cutting the plane up into strips like that. Now, on each strip, which is infinite in length, we can define a different function. Well, why can we do that? Well, if I draw a picture of a strip here, and imagine this is the place where the x-axis goes through it, then I can draw a piece of a function here. I can do that because a function has the property that no vertical line will strike it more than once. So in this strip, I don't have to worry about, well, I can draw a function. Let's just put it that way. I can do it and imagine that these are the endpoints of the interval where the function's defined. And on each one of these pieces, on each one of these little intervals, I can define a different function. All right, well then, assembling these strips into one function creates a piecewise defined function. That's all there is to it. A piecewise defined function. We just take these strips, and we indicate the top of the strip there, and there's the bottom of the strip, okay? We take these, we lay them next to each other, and together we have a function. Now, if we create a function in that way, the function will probably not have a simple algebraic formula. It will probably be a function that's defined in pieces, as you might expect. So let me give you an example of such a function. Here's one that I've drawn. There's a function that's in pieces. Now, let me go ahead and indicate here what the pieces are. First of all, we have this piece here of the function. You see it kind of curves upwards, and it goes between, what is that, -1 and 2. So there's a piece of the function. Here's another piece, a much thinner strip that goes from 2 to 3, and there's another function there, a little piece of line going downward to the left, to the right rather. Then there's a third piece, this piece over here, that is from, what is that, 3 to 5, and there's another function. Now I've put all three of them together, and I get this piecewise defined function. It consists of one piece here, one piece here, and one piece here. It is still all one function, all right? It is made up of three pieces, but it is a single function. How would I write such a function? Well, let's go ahead and decide how we should do this. How we write this. Well, we're going to write f of x for the function, calling it generic f function, and it's going to be a function that will be in three pieces, so I'll have to write it in three different ways. The first function piece, whatever it is, I don't care what it is right now, that's where that definition will go. And where is it defined? Well, if I look back at this picture, I see that this first function, whatever it is defined from -1 to 2. That's what this double arrow indicates here. So, the first function piece is defined for x's, which are greater than or equal to -1 and less than or equal to 2. And you might say, how do I know it's greater than or equal to and not just greater than? Well, look back at the picture a little more carefully. The picture in this piece has closed dots, which indicates that those points are part of the graph. Notice that this is an open dot here, this is a closed one here, and the last piece is open at both ends. Well, then continuing this, the second function piece will go from x greater than 2 and less than or equal to 3. Bringing the picture back, this second piece goes from x greater than 2. See, 2 is not part of this function because remember, a function can only intersect a vertical line at most once. It already intersects the vertical line once here, so it's got to be a hole here, and so it is. And then it comes down and includes this point on the right. So that's why I have x greater than 2 and less than or equal to 3. Finally, the third function piece will go x greater than 3, starting right after the point 3 that we had before. We start with x greater than 3 and less than 5. Why less than? Well, look at the third piece here. It is open at this end because it has to be. There's only one point that can be on this vertical line, and it's right there. So it's open there, but it's open at the other end also by choice, by the nature of the function that was created here. So, those are the three pieces. Whatever those functions are, I don't happen to know what those are, it doesn't matter. These three pieces are defined on these three separate intervals. Now, if we join those intervals together, since they all touch -1 to 2, 2 to 3, 3 to 5, the overall domain for the function is from -1, including -1, up to 5, but not including 5. So it's the closed interval from -1 to the open end 5. So I can get all of that from simply looking at this first picture, even if I don't happen to know the formulas which describe each of these functions. But you can see that the function is in pieces, and functions in pieces are written up this way. Well, let me take one that I actually do have formulas for to show you how this is going to work. Here's an example. F of x equals, and here's one, again in three pieces. Remember, pieces means anywhere from 2 to any number you like. Let's say that this is in just 3. Minus x plus 1, and that will work for -1 less than or equal to x and less than 1. And then the function will be 2, simply a constant function, when x equals 1, so that'll be 1 point. And then it'll be the function x squared when x is greater than 1. So it's clear here that the domain of this function, since these all link up nicely, is going to be closed at -1 because it includes -1 here. And then here it goes on to infinity, x greater than 1. So it goes to infinity. Okay, well, what does this look like? What's the graph of this function? Well, let me erect my axes system here. There's x and there's y. And I know that -1 is important here. It appears over here in the domain, and so also is 1. And I know that the function will go at least as high as 2 there. So let me indicate those on the y-axis. There's 2 and there's 1. Now we have to graph it in pieces in the same way that we wrote it up in pieces. For -1 to 1, so that would be from here to here. Now these dotted lines are not necessary when you actually graph it, but for the time being I'll put them in. On this strip, the function is -x plus 1. Well, if you know what the -x plus 1 function looks like, certainly it's a line with slope -1 and y-intercept 1. So it crosses here at 1, and it has slope of -1. If you want to draw this line fairly easily, since you already have the crossing point here, you just need one other point. So if I let x be 1, say, now you might say, oh, but x can't be 1. Well, for the sake of drawing it, I can use the 1. So if x is 1, this goes to 0. Now I know that that would be this point down here. but I can't keep that point because x is less than 1 for this part. So I'll put an open hole there, and then that will allow me to draw a curve, which is a line, like so, and I can even check this other endpoint. At minus 1, what is the function? Minus minus 1 is 1. 1 plus 1 is 2. So indeed this goes up to 2, and we have the point there. What is that? Minus 1, 2, and it is included in the graph. So this piece of the graph goes from here to here and doesn't include the point at 1. Now what happens at 1? When x is 1, the function's value is 2. So above 1, I have a point. And that's what I get from the second part of this three-part function. And so that's the point what? 1, 2. The third part says the function is x squared when you are greater than 1. Well, the key to graphing this is figuring out what happens when x is 1. You won't graph that point, but it'll give you the beginning of where your curve needs to be. When x equals 1, this is 1. Now we can't include that point, so I put an open hole. What does it look like? What does it look like from 1 onward? Well, it is simply the rest of the parabola, of the square function. Now I know that that curves upwards, so continuing that upward, maybe something like that. And you might even put a little arrow at the top to indicate it goes on forever. That just helps the picture convey the meaning of the function. So here's the graph I've composed from these three parts. What is the key to doing this graph? Each of these functions is easy to graph in itself. What you have to do is graph them on each of these intervals, and strictly on these intervals, keeping them very separate. The key is the breakpoints. Let me write that down. The key is what you might call the breakpoints, or the break x points, let's put it that way. The x values where the changes occur. Now there's only one breakpoint here. At 1 is where everything changes. From minus 1 to 1, it's all one function. Then at 1, it jumps up to here, and then the third function also starts there. So everything happens around 1, so there's only one breakpoint in this problem. But as you do more of these, you're going to want to look at the places where the breaks occur between the three parts. If you can graph what happens at those points, you'll be able to put everything together for the function. So that's a bit of advice. Now there are two famous examples of piecewise defined functions. Let me give you one, and then the other. Two famous examples. The first one. Well, we've seen this before. This is f of x equals absolute value of x. I said that would come back, and so it has. Absolute value of x, as you know, can be written in two parts. Actually, I'll write it in three just to be clear. The function is equal to x if x is positive, because the absolute value of a positive number is just that number. It's equal to 0 if x equals 0. And it's equal to minus x if x is less than 0. So there is a way of writing the absolute value function, which, remember, for calculators or computers may have to be written as ABS of x, in three parts as a piecewise defined function. And if you remember the picture of the absolute value function, and I hope you're starting to, there's y and there's x, it looks like that. Remember I said that this was a piece of the y equals x curve, and this was a piece of the y equal minus x curve. Now you see y. For x less than 0, it's a piece of y equals minus x. For x greater than 0, it's a piece of y equals x. And at 0, of course, it's just plain 0. So you can see this function, very familiar function. This part over here is the x greater than 0 part, and this is the x less than 0 part. And the absolute value function can be thought of as a piecewise defined function. The second of the famous examples is this one. And I'm going to write out several things here. First of all, it looks like it's made up of double brackets here. A little hard to draw by hand, but that is something what it looks like. A better notation is this notation, where I just have a little line underneath, sort of indicates a floor. In fact, this function is often called the floor function, floor of x. And what is its definition? Its definition is the following. It is the greatest integer which is less than or equal to x. Now you might say, what a very odd definition. I've never seen anything quite like that. Well, think about that for a moment. The greatest integer less than or equal to x. And while you're thinking, I'm going to write down the flip side of this. What's the opposite of a floor? A ceiling. So note, I'll define another function here, g of x, which I'll indicate with the ceiling. And we can even write it as the ceiling function, ceiling of x. What would that be? That is defined to be the least integer, which is greater than or equal to x. So, bringing back the last one, I have here the floor of x, the greatest integer less than or equal to x, and now I have the ceiling of x, the least integer greater than or equal to x. What is the idea here? Well, here's the idea. Very simple idea. Imagine you're looking at the x-axis, and here is an integer n, and here is an integer n plus 1. Maybe that's 9 and 10, or 57 and 58, two consecutive integers. And somewhere in here is your point x. Well, all that these two functions say is, take x, go down to the first integer underneath it. This, the floor of x, is equal to n. This is literally the floor. It's the first integer right below x. Likewise, n plus 1 is the ceiling. The ceiling of x is n plus 1. This is the ceiling. That's why they're called floor and ceiling. So x is always bounded on either side by an integer. And the one below is the floor, the one above is the ceiling. And of course, if x is equal to an integer, then it is its own floor and ceiling. Now in this course, we won't be talking about the ceiling function. We will, however, be talking about the floor function. But let me go ahead and do an example that indicates both of them. Example. Here is the number line. Let me just mark a few numbers on here for reference. There's 0. There, say, is minus 2. This won't be to scale. There's minus 3. And between minus 2 and minus 3 is a number, let's say, minus 2.1. And above 0, say, here's 3. Here's 7. Here's 8. And between 7 and 8 is 7.5. Now, let's go ahead and compute a few things. What is the greatest integer function of 7.5? That, of course, is the floor below 7.5, and that is, there's 7.5, its floor is 7. Easy to see. What is the floor below 3? Well, 3 is its own floor. It's an integer. What is the floor below minus 2.1? There's minus 2.1. What is the first integer below it? That's minus 3. See how easy this is? If you have the picture in mind, computing the floor or the greatest integer, now this is the greatest integer function on 3, and this is the greatest integer function on minus 2.1. But frankly, I like the floor version better. Okay? And that is the terminology I will use in the course. I won't indicate ceilings because we won't be talking about ceiling function in this course, but I think you can figure out the ceiling for all the numbers that we've just seen. Finally, the very last piece of this bit, the graph. The graph of f of x equal the greatest integer function, also known as the floor function. What does it look like? Well, it's a very interesting picture. Let me mark off 1, 2, 3 here, and then on each of the axes, let's go to 3. There's x and y. This is minus 1, minus 2, minus 3, and then minus 1, minus 2, minus 3 there. Now, the integer put into the greatest integer function, or the floor function, is equal to itself. So 0 goes to 0, 1 goes to 1, 2 goes to 2, 3 goes to 3, etc. Minus 1 goes to minus 1, minus 2 to 2, and minus 3 to 3. Of course, this will then continue off to infinity. Of course, and if you connected those dots, however, you'd have a very wrong picture, because everything that is interesting happens between the integers. What happens to 1/2, say? When x is 1/2, what's the greatest integer less than or equal to 1/2? Well, that's 0. So that means the value here is 0. In fact, the value is 0 for everything in here until you get to 1. That's an open hole, you pop up to 1. Then everything is going to stay flat till you get to 2. And you pop up to 2. And then similarly, the steps go on in both directions forever. This is what's called a step function. Or if you like, it's an infinite staircase. And it is a function in pieces. Although I didn't actually write it in piecemeal form, it's a function in pieces. That's the reason I put it here. Okay, I think it's time for you to practice this piecewise defined function family of functions and to see that you can graph them and make sense of the pictures. Before we go on to the next topic that I want to discuss, which is how do we take these functions and alter them in the way that I indicated before, shift them from side to side, compress them or stretch them, or maybe reflect them across one of the two axes. Before we do that, I thought I would do a few simple exercises. So here are some exercises explained. So let's look at this first one here. Here's an exercise. Here's a function given to us, f of x equals 1 over the square root of x squared minus 4. And before we do anything with this, we want to know what's the domain of this function. Because only on the domain of the function does the function make sense. So, we look at this and say, what could go wrong? Well, we have a division, and we have an even root. So we have both problems. Now, the even root requires that what's underneath, the x squared minus 4, be either 0 or positive, because even roots require 0 or positive. However, this root is in the bottom of a fraction, so the 0 case is not allowed. So with that in mind, we can start our solution by saying we need x squared minus 4 to be greater than 0. Now that's the way I suggested you do these when we looked at domains earlier. We need x squared minus 4 to be greater than 0. Well, now we follow this through. We say, well, what does that mean? That means x squared must be greater than 4. That's okay. Now we take the square root of both sides, and I'll actually write it in. The square root of x squared, of course, you remember, is the absolute value of x, and we want that to be greater than the square root of 4, which is 2. Absolute value of x greater than 2. Let me see if I remember what absolute value was. There's 0. Absolute value is the distance of x from 0, so I want numbers that are greater than 2 away. That can either happen to the right like this, or it can happen to the left when you go below minus 2. Okay, go above 2 or below minus 2. Well, putting those two pieces of information together, and I'll do it on another sheet here, that means, I'll rewrite that, absolute value of x greater than 2. This means x is less than minus 2, or, because it can't be both at the same time, x is greater than 2. In other words, x is in minus 2, or minus infinity to minus 2 open, that's the first one here, or it is in the interval from 2 to infinity. And that defines the domain of the original function, which recall is this, 1 over square root of x squared minus 4. So as long as our numbers come out of the set of numbers that are less than minus 2 or greater than 2, we have a domain element that we can use in this function. Okay, good. That's one exercise. Now, here's another one. Given the graph of function f, here's the graph. We have the curve going up like this, and when we're given a graph, we have to just accept what's given to us and make reasonable deductions from the picture, because we're not given a formula. It looks like it's asymptotic, like it's coming down to the x-axis, but never reaching it, and it looks like it's going upward here, but never crossing this minus 1 line. That's what's dotted in here, the vertical line at minus 1, and then it does the same thing on the other side. It also seems to pass through the point 0, 1. Now, what are the questions here? The questions are, what's the domain of f? What's the range of f? Is it increasing and decreasing, and where do those things occur? And is it even or odd? Well, we're already working with the picture, so we have to look at the picture and ask ourselves, first of all, the domain. The domain, remember, is the shadow on the x-axis. Well, how far to the left and the right does this go? Apparently, it goes forever, to the left and to the right. There is only one point in the picture, this minus 1 point, that looks like it is not part of the domain. Looks like the curve never crosses over here. So, with that information, my solution, I start writing things down. It looks to me like the domain of f is going to be using that set builder notation again. All the x's in the real numbers such that x is not equal to minus 1. Because from the picture it looks like minus 1 is the only number that's left out. Now what about the range? The range would be the shadow horizontally onto the y-axis rather. Well, notice that this curve never seems to go below the x-axis and never seems to touch the x-axis. But it does seem to go upward forever. It looks like these pieces continue forever. So I would guess that the range is the set of all the values that are above 0 and going on to infinity. So writing that down, the range of f then would be an interval, nice simple interval, above 0, starting at 0 but not including 0, and going off to infinity. Of course, this is in the y direction, so this is a vertical picture. All right, what else would we want to know about this function? We want to know where it's increasing and decreasing. Well, that's easy to see. If we remember that we are moving from left to right again, increasing is this piece, and the other piece is decreasing. So it seems to be increasing from minus infinity out here up to minus 1, but not including that. And then on the other side, from minus 1 to infinity, it seems to be decreasing. So I can say it's increasing on the interval from minus infinity to minus 1, open, because minus 1's not in the domain. And it seems to be decreasing on the interval from minus 1 to infinity, starting at minus 1, but not including minus 1. Also, the question was, is it even or odd? Well, even would mean symmetry across the y-axis. Clearly that's not true. There's a point here, say, but there's no corresponding point over here. Is it symmetric across the origin? If I took a point here, is there a corresponding point here? No. So the answer to that question is not even, not odd. So from the graph, I've been able to get all of this information. It is limited because I don't have the actual formula for the function. I have to go strictly by the picture, which may or may not be accurate. But this is certainly a way to answer questions like this. All right. Well, let's do one more just to practice doing some exercises here. Here's one. Here's a function given to us. F of x is x over x squared minus 1, a rational function. What's the domain of this function, and is the function even or odd? Well, let's find out. Solution, let's look at the domain first. Again, we ask ourselves, what could go wrong? Well, there are no even roots here, but there is a division. So I want x squared minus 1, so I should write this in, because I'm trying to be consistent here. We need what? We need that x squared minus 1 is not equal to 0. Because if it were equal to 0, we'd have division by 0, and that's undefined. Well, x squared minus 1 not equal to 0, we just continue and analyze this. That means x squared is not equal to 1. All right, just move the 1 to the other side. And then I take the square root of both sides, and of course I know what that is. I want x not equal to minus 1 or 1, because those are the only two numbers. Which one squared give me 1? So those are the only two numbers that have to be omitted from the domain. And so I can write down that the domain of f is, using that set builder notation again, the set of all the x's in the real numbers such that x is not equal to minus 1 or 1. So there's the domain of this function. And that was fairly simple. All right. Now I want to know whether it's even or odd, and I don't have a picture to work with. So I'll even write that down again. Even, odd, question mark. Well, let me rewrite the function here with boxes, because I want to apply the even-odd test. So the function is f of box equals box over box squared minus 1. The actual statement uses an x, but we can use a box to understand what's going on. Now to check evenness or oddness, remember the conditions? I'll put them over here. F of minus x is the key object that you check. If it is equal to f of x, it's even. If f of minus x is equal to minus f of x, it's odd. Those are the two conditions. So the thing that you need to check is, what does f of minus x look like? So that's what I want to do here. I want to evaluate f of minus x. Well, using my boxes, it's easy to see. It's minus x over minus x squared minus 1. Now I'll do some simplification. Minus x on the top. Minus x squared is the same thing as x squared, of course. X squared minus 1. And one more simplification, I'm going to factor that minus out of the whole thing. So I have minus x over x squared minus 1. But wait a minute. X over x squared minus 1 is f of x. So this is minus f of x. So f of minus x is minus f of x. That's condition 2 here. So this is an odd function. I'll put it over here. Odd. So the original problem was this. What is its domain? Is it even or odd? We found the domain with a little bit of effort here. And then we checked if it was even or odd, and it turned out to be odd. Well, there's just a couple of examples which I hope will whet your appetite for doing a few more of these problems on your own. I think we'll stop there and go on with the rest of the development of graphing techniques when I come back.